Hello, everyone. In today's video, we're going to be going over how to do the neutralization lab. So right here, you can see that I have Excel and I have graphed, or I've put all the data points for one of the water samples or one of the water trials and one of the neutralization trials. You'll see my times go from -5 minutes to 5 minutes. And before that 0 mark, our mixing mark, we have temperatures of cold and warm varying, and then temperatures of acid and base varying. So the first thing we're going to do is we're going to go ahead and make a graph. So we're going to insert, we're going to click on our first two. We're going to insert a scatter plot, and it should look something like that. Then we're going to go to select data, select data. So click on the graph itself, right click or double click and go to select data. And we're going to add a series. The first thing I had on there was cold water. This one is going to be called warm water. My X values are going to be the times. And then my Y values are going to be, obviously, the warm water temperatures. Make sure to click on the entire column and then press OK. Now I'm going to go ahead and edit this one to be cold water because we're going to need a legend here. Okay, we're going to add one more. The last one is going to be mixed. And we're going to get our X values, again, getting that whole set of X values, and then our Y values, getting the whole set of Y values, and OK, and OK again. And we should get a graph that looks something like this. Now, we want to zoom in on our data, and that's going to be the first thing I do. So I'm going to click on my Y values, double click or right click, and go to Format Axis. And I'm going to start at about 20 and see what that looks like. And that's pretty decent. We can also have this axis right here cross over here instead of in the middle. We can do that by clicking on this axis, going to Format Axis, and we want the axis to cross, so vertical axis crosses it, and we're going to do at axis value, -6 minutes. So now it looks something like that instead. Just because it looks a little bit neater like that. I have done the graph where I've kept it in there, so this is just another example. You can do it either way. I don't really care. Okay, after this, we're going to add in trend lines. So we're going to click on one of the data sets, and we're going to go to add trend line. And we have to do that for each one. And then once we have the trend line, we're going to click on it, right click or double click to go to format trend line, and then display R squared and equation, and make sure that we do that for each one. And make sure we give ourselves a little bit of room so we can see exactly what's going on. Okay. Next, we're going to add in some axes titles. So go here. If you are on a Mac, you might have to go into chart design and do it through here. You'll just do primary, then vertical. And we're going to name it. This is, we can name it several different things, but we are calibrating our calorimeter right now. So we can call this a calorimeter. Oops. Calorimeter calibration. I can't spell calibration. And then on our y-axis, we're going to have our temperature. In degrees Celsius. I think I'm spelling that right. And then time in minutes on our x-axis. We're also going to want to add in a legend so we can see exactly what's going on I'm going to make my graph a little bit bigger, and I'm going to remove any of the trend line thing. So you click it once, and then you click it again until it highlights that, and then you can delete. Okay. Oh, that's not too bad. Am I missing anything from this? Nope, looks good. Okay, so that is our first graph that we need to have in here. I see this is a little bit weirdly placed, so I'm just gonna move this a little bit further over. And okay, we want to do the same exact thing for our neutralization data. So go ahead, insert scatter plot, clicking the first two lines, and then add in, sorry, select data. Go ahead and edit this. This is the acid, or we can just put HCl in there. And we're going to add NaOH with our X values there and our Y values there. And then add one more. We call this mixed or neutralization. I'm just going to go with mixed. And there's our, oops, too far. Our X and our Y. That's where we're definitely trying to figure out what's going on here. Okay, there we go. That looks much better. Okay, and again, we're gonna start this at about 20 degrees again. So format axis started at 20. And that zooms it in a lot better. And then we're gonna move this over to -6 again. And again, you can keep it in the middle if you would like. Entirely up to you. And then we're gonna add in our trend lines. And our legend, making sure to remove that. We're gonna add in a chart title and axes titles. And this would be our neutralization graph. And then this is going to be, again, same thing. This is going to be our temperature, degrees Celsius. And our time, it's larger, like so, if we would like. So those are our two graphs. Same size, that's work. Again, before I had left those in there like that, and that should be fine. This is just an example from last semester. So you can do it either way, whichever one you like better. Okay. After that, we need to start using this information to find out how to solve for our calorimeter constant and the heat of our reaction. So let's go over how we do that. So first, we need to figure out how much water, or sorry, how much heat was lost by our water. So we're our warm water, and how much heat was gained by our cold water. So we're going to do that with our graph itself. So back up. So one of the reasons, I know a lot of you guys were like, oh, why do we start this at 0? Well, this is now our y-intercept. So if we put 0 in any of these graphs, it'll tell us exactly when it hits the x-axis. And that's going to be our temperature. So when we look at this, if we put a 0 into here, we see that our y-intercept is 32.37. So we can essentially assume that that's the temperature that our hot water is right before we mix it in with our cold water, which is at 23.57. And then our mix, when they have kind of equilibrated, it's going to be at 26.74. So our T initial for our hot is, in this case, 32.37 degrees Celsius. Our T initial for our cold is 23.57 degrees Celsius. And our T initial, or sorry, our T final for our mix, which is our both, which is both, is going to be the 26.74 degrees Celsius. So that's the data we're going to use to actually solve for the heat lost by our warm water, the heat gained by our cold water. So our delta T for our cold would be the 26.74 degrees Celsius minus 23.57 degrees Celsius. And then the delta T for our hot is going to be 26.74 degrees Celsius minus 32.37 degrees Celsius. So these delta T's are going to then go into Q of hot, Q of cold. And keep in mind that each of these were 50 milliliters. So adding them together, we have a total of 100 milliliters. So our mass for both of them is going to be 100 grams. So that's how we're going to actually solve. We're going to solve for our Q hot. We're going to solve for our Q cold. And what we end up getting we should get approximately for our Q cold, we should get 1,326.3 joules. And we should get for our Q hot, negative 2355.6 joules. So the heat loss between them is going to be the difference in these numbers. So we're going to do essentially add these two together and take the absolute value. So our delta H of our delta H lost, so how much we lost here, is going to be 1029.3 joules, which we will then divide by our delta T of our cold. So this right here. To get a calorimeter constant of 324.7 joules per degree Celsius. So that is the calorimeter constant that we're going to be using for the rest of these calculations. So I'm going to go ahead and write this down. So we can then use that for other parts of this problem. Okay, so now we're going to be looking at the actual neutralization reaction itself, and finding out what our actual delta H of our reaction should be. So we're going to look at the heat absorbed by the solution, the heat absorbed by the calorimeter. So we're going to do the Q of our solution. We're going to do the Q of our calorimeter. And then the Q of our neutralization reaction will be equal to the negative of those two added together. And then our delta H of our neutralization reaction is going to be equal to the Q of that neutralization reaction divided by the moles of HCl. We're going to use the moles of HCl here because our HCl is going to be our limiting reactant, which you probably have already realized at this point. So Q of our solution is going to be the mass of our solution times by the specific heat times by the delta T of our solution. The delta T of our solution we're going to find from our graph. If we have different initial temperatures for our acid or our base, we will use the value, or we will use the average between those values. Okay, so let's look at that graph. Bring it back up so we can actually see what values we'll be using. Again, we're going to use our y-intercept. We're going to put 0 in, and that tells us that our T final for our mix in this case is 28.16 degrees Celsius. The T initial for our HCl is 23.87 degrees Celsius. And our T initial for our NaOH is just 22.3. So if we take 22.3 plus 23.87 divided by 2, we get a T initial of 23.09 degrees Celsius. So that'll be our initial temperature. This will be our final temperature. So our delta T for this reactor, for our solution, will be our final 28.16 minus our initial 23.09, giving us 5.07 degrees Celsius. Our total solution volume, we had 50 milliliters of 1 molar hydrochloric acid and then 50 milliliters of 1.05 molar NaOH, which is why our HCl is our limiting reactant. So we are going to add those two together. So our solution is 50.0 milliliters plus 50.0 milliliters, which gives us 100 milliliters. However, our density of this solution is 102 instead of just the 100 that we used in the last part, because our last part right here was just pure water. So we're going to take that 100 milliliters, multiply it by the density, 102 grams per milliliter, to get 102 grams of our solution. And then that is going to go into the mass of our solution. Our specific heat of our solution is going to be 3.822. Joules per grams times by degrees Celsius. And our delta T is what we just solved over here. Wrong direction. The 5.07 degrees Celsius. So if we take our 5.0 degrees Celsius times by the 102 grams and then times by 3.822, we should get a Q of solution equal to 1976.5 joules. Our calorimeter constant, we're going to take our, sorry, the heat of our calorimeter. We're going to take our calorimeter constant, 324.7 joules, multiply it by the delta T of our solution, the 5.07 degrees Celsius. That gives us 1646.2 joules. Add that to the 1976.5, and we get a value of 3622.7. So our Q of our neutralization would be negative 3622.7 joules. That then can be taken and divided by our moles of HCl. Remember that we had 50 milliliters of HCl, which if we divide that by 1,000, and then multiply it by the molarity, we get 0.050 moles of HCl, which we're then going to divide to give us negative 72454.6 joules per mole. And then dividing this by 1,000 to get it into kilojoules per mole, we get negative 72.5 kilojoules per mole for our enthalpy of neutralization. That's all the calculations we have for this. They're not super hard calculations, as you can see. You just have to have the graph, which is why I wanted to show you guys how to graph it first. If you have any questions, please let me know. And have a great weekend.